I welcome you to this particular course code, which is Math 302, with course title, uh, with course title, Theory of Modus. This course code has a course title, which is known as Theory of Modus. So, if this is the course title, so what do you need to understand under this course? So, at first, we need to understand modus. Okay, let me just say under this course itself, the first thing we need to understand under this math 302 course is we need to understand the concept, and let me just say the basic concept of modus. That's the first one. And then the second thing you need to consider now is what we call the linear mapping. The linear mapping will also be discussed under this course. And then at the same time, the third thing that we need to consider here is actually the bilinear and the quadratic form. So you need to understand the concept of these three clearly. They are very, very important. So I believe that I think there are little examples on this whereby you need to calculate some um, to do some several calculations under this linear mapping. But you see, as for this modus, we actually have many things under it. You must understand the definitions for modules. You must be able to give definition for this. At the same time, there are a lot of proofs under this modules which you must clearly understand. Then after that, you also need to understand the basic concept of submodules. So that's just the major pattern to this course. So if you can actually understand the definition of modules and as at the same time you actually take note of the most important theorems or proofs under modules. Then after that, when you actually have a clear understanding or a clear picture of all those theorems and proofs, then the next thing for us to consider now is what we call the submodules. This submodules also has its own definition and it also has its own theorem too. So most of the theorems you must also know them along with their proofs. Okay, along with their proofs. So then after this particular submodules, then I think we also have another thing to consider under it, which is the quotient modus. See, all these things you need to understand it clearly. We also have under this we have the quotient modus. So I'm just trying to give a clear picture of what you need to understand under this course as a whole. So the first thing is the modus. You need to understand the definitions, the proofs, the definitions and some of the important theorems, and you must also know the proofs to those theorems. We also have some examples. You can show them with examples. You can show this particular section here with examples. So you do the same thing for submodules. State the definition. You must be able to state the definition for submodules, and you must also be able to state most of the important theorems and then provide the proofs with it along with examples. The same thing goes with quotient. You must be able to state the definition and some of the important propositions. Let me just say the lemmas you have under it, but majorly I would love you to understand the basic propositions under this quotient modus, whereby I think we also have I think we have one of the important proposition under this quotient modus. I think we call it isomorphism theorem. We have the theorem guiding it. So I think it actually has its own proof. You must know how to show the proof. The proposition which states the first isomorphism theorem. We also have the second isomorphism theorem under this quotient modus. We also have the third isomorphism theorem under this same quotient modus. So that means you need to understand the first, the second, and the third, along with proofs, and at the same time, along with what? With examples. Then after you've covered these three, that's when you will now have to understand the basic concept of linear mapping. Then you move straight to linear mapping. And looking at this linear mapping, we have a lot of theorems too guiding it and some examples. So I think there are some examples that requires a little calculations whereby you introduce matrix, you add matrix. Sometimes you need to multiply it by you need to find the basis and all those stuff. So I will also make sure that I try my possible best to explain this clearly. Okay. Then under this linear mapping, when you understand the basics theorems under it with examples, then you will still need to consider what we call the rank of linear mapping. Let me just call this LM. You must also understand the concept of the rank. Okay. You must also understand the rank of linear mapping. You see, this rank of linear mapping, they have their own definitions along with proofs. Sorry, they also have their own terms along with proofs. So you just have to take the important one and then you study it well and make sure you know one thing, understanding matters. So you need to understand most of these terms. If you don't understand it, forget about it. You will be able to apply it to any kind of problem or any kind of questions that you might come across with. So understanding matters in that case. So after this, then after you've actually understood the concept of this particular rank of linear mapping, then you are now free. Then that is when you can actually move straight to this bilinear and quadratic form. Okay, by linear and quadratic form you must understand the definition as well. Okay, you must understand the definition as well, and at the same time you have a lot of theorems under it, or let me just say a lot of definitions, and most of the definitions can actually provide proof for it, but you need to consider the important proofs. And how will you know the important theorems to study? So it's better for you to study more theorems than you looking for the most important ones. So that's it. To be on the safer side, you need to you need to get yourself you need to familiarize yourself with a lot of theorems, but not just anyhow theorems, a lot of important theorems. So I believe you actually have access to the materials. So I believe you can actually there are some if you still have the material with you, I think for my 302 there's a material which Dr. Ibo dropped for us then. So I think if you can actually go through the material, there are some theorems that are actually asterisk some of those theorems. So you just need to take note of those theorems and then understand it clearly. Not by cramming. You don't need to cram it, you need to understand it. So as I keep dropping most of this video series, most of the tutorial video series, I'll make sure I try in as much as possible best to break each of these. I'll make sure I break it down one after the other, including the definitions, the theorems, and their proofs. In fact, along with examples. I'll make sure I try my possible best to do that. Um, so for this bilinear and quadratic form, we have a lot of examples under it. A lot of examples, a lot of examples. So in order to speed up this class, I will try in as much as possible to add a PDF. Maybe on this page, I will try to bring out a PDF to make it more faster. Then I will just show you most of the definitions, and then along with theorems, all I'll just do is to explain it and then try to draw my pen on it and then explain it clearly. Okay, that will be the best thing. Because if I want to say I want to write out if I want to write out most of the definitions now, okay, definition, let's say I want to write out the first definition, then I will now have to write state the definition before I will show the proof. It's going to take a lot of time. But I have a particular PDF that has most of this content that we need for this three sections: modules, linear mapping, bilinear, and quadratic form. I have a particular PDF for it, or let me just call it lecture notes, exactly based on my 302. So I already have lecture notes. So all I'll just have to do is to present the PDF in a page here, just of this size, and then whatever explanation I want to make, I'll make it on the right hand side here. So that will be the best thing. So I think we also have under this bilinear form, I don't think that's all. We will still have to consider a particular topic under it, but it's not really necessary. We call it the inner product space. The inner product spaces. So I think this is also part of this particular course code with this course title theory of modules. So it's actually under it, but it's not really necessary. If there's still enough time to do that, I'll make sure I include it. I'll make sure I include it. So I think that's all we need to consider for this course. So in our next video, I'll make sure I try as much as possible to present the PDF and then drop it along with examples. But before I do that, let me just go ahead and explain what, okay, the course title is Theory of Modus. You've been wondering what is modus. If I just ask you what is modus, what can you actually say about the course? You know, when let me just give you a very clear or a very simple definition to this. When you are referring to modus under abstract algebra, whatever I can actually just do, or under algebra, how do you refer, how do you give a very simple definition to modus? You can actually say that modus are just like a generalization of the vector spaces in linear algebra. That's all. They are just like a generalization of vector space in linear algebra. So when you are dealing with linear algebra, most at times in linear algebra we actually focus more on matrices, vector spaces. You know, in that case, I can actually, okay, that means I think in that case we have more vector spaces under this topic here. Yes, under this linear mapping, more vector spaces, and also under this bilinear form, and in fact in quadratic form too. We have more of it in this case. But I think under this modules, we have a lot of theorems which will not really lead us to presenting matrices or any other vector spaces. But at least there are some examples that I can actually present in terms of vector spaces under these modules, under the most of the theorems and the, or let me just say most some of the properties of modules, or some of the relationship between scalars and the modules M I want to use. So don't worry, I'll just try to make sure that I explain it clearly. So let me come again with this definition. We are dealing with modules. We can actually say that modules are just like a generalization of the vector space in linear algebra, simple as ABC. And I can decide to add more to the definition. I can say that in which the scalar is taken from an arbitrary ring R, an arbitrary ring. I think there's a way we used to write it. An arbitrary ring R, okay, which is rather from a field F. We don't consider the field F in this case. So for this course, we need those knowledge that we obtained from linear algebra, because if you still don't have idea on 202, you find this course very very hard to understand. 202 is just 202 is a course code whereby we have the course title as linear algebra. And I just gave you a definition for modus now. I just said that modus is just like a generalization of the vector spaces that exist or that we have already in linear algebra. I repeat, modules are just like a generalization of the vector spaces in linear algebra. So imagine if you don't understand 202 clearly. So how will you be able to flow with this course? So it will be very, very hard for you to do that. Very, very hard for you to do that. So now I've just given you a very clear definition of, or a very clear picture on what modules is actually talking about. But just take note that it involves taking a scalar, okay, from a particular ring R, or you just say a scalar is actually taken from an arbitrary ring R, so rather than from a field. So that means in this case you are not considering a field, you are only considering a ring, an arbitrary ring in this case. So now looking at this modus, we have an official definition for it. They are of two parts. Yeah, they are of two parts. The first one is what we call the left R module. We have what we call the left R module. We used to represent it as I can write it as L, then put a dash, and I put R. So after this R, then I put a small dash in this and I write module. Okay, we call this a left. We call this how do I put it? A left R module. So you see this left R module, you must be able to state the definition for it. And to state the definition, you must be able to show that it satisfies some axioms, some conditions. How many conditions are there? I think those conditions are up to like four. If you check some other tutorial videos, it might be up to five. I think the last one, but majorly for um, major axioms or major properties that you are going to see most of the time, there are just four. So if you want to show the definition for left out module, that means in modules we have to, if you want to define a module, aside from the definition I gave earlier, You need to define it officially or in a very smart way. So to define a module, you need to give a definition for the left out module, and at the same time give the full definition of the what, of the right out module. So it's better you just write this as left, then you put, you can just write this as left, then write left out module, while this will be written as right r module. So for this left out module, if you want to define it, if you want to state the definition, you must be able to show that it satisfy four axioms, four important axioms, okay? Like the first one I will explain, the second one I will give you the four axioms, okay? If you can actually state the four completely, then that means we are halfway to the final expression for the definition. So you must be able to show that it satisfies four properties here, show the condition for the four properties. And at the same time, for the R modules also, it also has four conditions. You must be able to show four conditions for it too. It must satisfy four conditions. What are those conditions is I will also explain it clearly to you. So if you can actually show the eight conditions successfully, then that means you already understood what, that means you'll be able to give what you need as definition for modules in that case. If you only show for left arm module and you decided not to show for right arm module, then that means you are halfway to your full, giving you your full marks. So it's not really possible that way. So I would advise you to give the full definitions. State the definition for left arm module and at the same time state the definition for right arm module in that case. And you see all this left arm module, you feel like, okay, what is left arm module? Don't worry, I'll make sure I show it clearly in this case. You'll be wondering what is right elbow do? How does it look like? How does it sound to you? You feel like I don't know what that means. Don't worry, I'll make sure I state it clearly to you. So before I move straight to the next, before I end up this video lesson for series one, let me quickly state the definition to be on the safer side. So we have modules in this case now. Modules. So looking at this, I want to start with the definition. Okay, definition. Okay, define a module. So how will you start it? So to define a module, I'll just advise you to just consider two asterisk. Okay, I have two things to consider. Okay, so the first one is the left arm module, and the second one is what? Is the right arm module, right? So we need to start with, if you want to give a definition, you can try to start with let R be an arbitrary ring. That's the first thing we need to consider. Okay, that's the first thing we need to consider. Then looking at this, if you actually want to state the definition for modules, you always or you assume that we actually have an arbitrary ring R, or let R be an arbitrary ring. Okay, I already said it. Okay, we are only considering an arbitrary ring in this case, but these arbitrary rings must actually comes with an identity. It must have an identity. Just take note. It must. It's a must. It must be an arbitrary name with identity. It's a must. Okay? So this be the first thing that should come to your mind if you want to take the picture for modules. And then if you have actually, okay, I've introduced an arbitrary ring, right? So then I can now go ahead and state the left out module. So that's where this comes in. Okay, I can decide to say that, okay, a left R module, you see, I've started with that. So since you've actually called for an arbitrary with identity, if you now want to state for the second one, which is for the right a right out module, do you still need to repeat this? No. You've already brought in your arbitrary ring with identity in the definition. So you don't need to repeat it here again for the right R module. So that means for this second asterisk, after writing out the four conditions here, for this second asterisk, all I'll just have to do is just go ahead and say, okay, a right R module, then I'll continue with the definition. So what do I have to write after this? Okay, a left arm module in this case, or okay, let me just put that. You can say a left arm module, or you pronounce it as this thing I'm just writing on the screen. So anyhow you feel like pronouncing it, you can say a left out module, or you say a left module over an arbitrary ring R. Okay, a left out module, you need to show that it's an abelian group. Okay, and to show that it's an abelian group, it must satisfy these four properties. So a left out module is an abelian group. Okay, it's an abelian group. Let me say, okay, let me call it an abelian group M, module for M. Okay, it's an abelian group which also has a scalar multiplication, an abelian group together with a scalar multiplication. So that scalar multiplication, we always take it as sometimes you can use it as small letter R. I think in the material, in Dr. Abel's material, it is R that was used. In other textbook, a scalar multiplication can be denoted as A. Okay, it can use A. In some other textbooks, they can decide to use S. So just take note of that case. So a left hand module is actually an abelian group. I repeat, a left hand module is actually an abelian group. So I call that abelian group M, capital letter M. Okay, and this left hand module is always an abelian group together with a scalar multiplication. Okay, so that means after writing this, I must state that scalar multiplication. So let me just put it as saying, okay, let me just put it in this statement together. Okay, together with a scalar multiplication. Okay, so then that is where, instead of going straight to the, okay, I'll just go ahead and state an abelian group together with a scalar multiplication. Okay, that means most of the condition I want to state now, the four conditions, that means it actually shows an abelian group, and at the same time it will always be multiplied by, it will always show a scalar multiplication, that is A is multiplying something, or let's say something is multiplying R. So in that case, so in this case now I want to make use of A, scalar multiplication. I want to use a scalar representation. My scalar representation here for this explanation is A. I think in the material it is R. So if I'm using A and in your own material you are seeing R, you should know that we are still referring to the same thing. So you don't need to be confused about that. So now that I've stated it, okay, a left arm module is always an abelian group. Take note. And if it's an abelian group, it always comes together with a scalar multiplication. Okay, that means I introduce two things, an arbitrary ring R. I can see this R, and at the same time I can also see this abelian group M. So then how do you represent this mathematically? You just introduce an arbitrary ring, and at the same time you already said the left hand module is an abelian group. So how can you show you the mapping? How can you show the linear mapping? Which simply implies that, okay, it's actually under scalar multiplication, right? So the arbitrary ring R together with the abelian group M, we always map to um the abelian group M itself, or to a module M. Okay, to a left module M in that case. So if you actually have this kind of mapping, it must satisfy four conditions, which satisfy the following. So what are the conditions? They are just four in numbers. Okay, so to make it more okay, you can just say we satisfy the following axioms. Is that clear? We satisfy the following axioms. So the next thing for us to do from here now is to state them one after the other. What is the first statement? I actually introduce an arbitrary ring together with what? With an abelian group. Okay, normally I already introduce an arbitrary ring, and then I now have a left out module which is an abelian group together with a scalar multiplication. So then it will always map to a module M in this case. Now, and it must satisfy four properties like I said. So what are those four properties? So then you have to list them out. The first one, if you can actually state for left arm module, to state for right hand module is not, to right arm module is not going to be a hard thing for you to state. So you just understand the first four I want to state here, three, four. So it must satisfy these four axioms. What are those four axioms? I'm dealing with the left arm module, right? So I'll just take, okay, I have four axioms. That means I have module one, the first one, module two, the second one, module 3, and then I also have module 4, right? So the first axioms, this is for the left R module M1, also for the left R module M2, for the left R module 3, for the left R module 4. Okay, so now we have four axioms. What are those four axioms? Such that we have the left R module 1, such that there exists a scalar multiplication together with an abelian group, right? So that means a scalar multiplication that I'm using here is just A. If you want to use R, you can go ahead, but I'm not using R in this case. So I want to use A. Okay, this is a scalar multiplication. Okay, a scalar. This is my scalar representation. But it is a scalar multiplication. That means it's going to multiply an abelian group. So an abelian group can actually comes in terms of addition. So that means I can decide to have, if I have an abelian group M, I can decide to pick an element of this. I can pick a smaller element from this abelian group. Let's say I want to pick a small m, and then I can pick the next letter after m. I want to pick two elements, m and n, which is actually a subset of the abelian group or an element of that abelian group. So I have mn, right? So I just brought in a small element or an element from the abelian group, that is m and then the small n. So how can I play around these two small elements? Then that means I will come here and I can actually go ahead with addition. I think that is, if you actually understand the um I don't think from our 201, which is the abstract algebra that we did back then, you can still go and recall what an abelian group is. Go and check what an abelian group is in that case. So first I want to take the addition. It actually satisfy under addition. This is an abelian group under addition. I added the two elements together with a scalar multiplication A. So with a scalar multiplication, I can just use A in this case, put it in the bracket. So that if I'm using A is already here. If I'm using R, I'll put R in this case. So I think this is clear. This for the first one. So if I have something like this, you should know that it will surely satisfy. I think this is distributive. So okay, is it distributive also? I can't really say. So this is A times M. It is equivalent to, you just go ahead and solve this. It's not something that is really hard or special. A times M is AM plus A times N is AN. Then you are done with the first one. So now let's go with the second one. What does the second one says? The second one is now as if I'm not having, the second one now is that I just want to take just one element in the abelian group, just one element. I don't want to pick two. Take note, for the first one, I pick two elements. For the second one, I'm only picking one in this case. So that means if I want to pick just one element, I would automatically pick two scalars, scalar A and scalar B. Okay? I want to pick scalar A and scalar B, where A and B are scalar representation in this case. So if I want to pick two scalars now, that means I will go ahead and add the scalars together, okay, in this case, and then multiply it with the element I pick from the abelian group. G standard logic. So in this case, I added two elements from the abelian group together with just a single scalar multiplication, with just a single scalar representation rather. Then I decided to solve it and I have this first one. But for the second result, I want to consider just two scalar representation and then multiply it together with just a single element from the abelian group or from the module M that I just brought in, the let out module M. So now in this case, you should know what this will give us. If I multiply this now, it is also be equivalent to AM plus BN. No, here in this case, I only have just one scalar. Here I have two scalars representation. Now what happens in the third part? In the third part, I'm not considering the addition. The same procedure for step 2 and 3. For the module 3, for the LM2 and LM3, I'm still considering just one element from the big module M, and I'm still also considering the two scalar representation. So for this, I'm not adding. I will not add the two scalars together. I'll just go ahead and join it together, which is the multiplication of the two in a bracket. Then together with the what? Together with the element that with the element in the big module M, or in the abelian group M that we just present here in this, that just presented in the definition. So if you have this case now, that means this is also equivalent to what? This is also equivalent to, okay, what if I have A, B, M, and B. The bracket is within the first and second representation. This thing is still equivalent to, if I'm not considering the first and second, the highest thing I can actually the last thing I can actually, or the only way to consider these products now is to pick just this. You can't just say you want to put the bracket here and then you close it here. It does not really make any sense. If I can actually have the first and second, the only choice I could have left is to pick the second and the third. So this and this are still equal. Just like saying, if you have two times three multiplying each other here, then times five. So is it equivalent to two times three and five? Okay, let me just put it as two open bracket three times five. Is it not equivalent? Let's check. Two times three is six, then times five is 30. Now, what if I multiply three and five first? Three times five, three times five is 15, then times two is still 30. So you see that it's satisfied. Okay, that is correct in that case. So what about the last one is actually where we have the identity part. Okay, this last one here is actually where we have the identity part. So that is when you have an identity, that means is that you use E. We used to use E to represent an identity, which is representing one, is a unit value in that case. So is that I use E, or I go ahead and use one, okay, or I use I in that case. So in this case now, I really want to use um I'm using one to represent the identity element. Okay, one is going to multiply just M, which is a member of M. In this case, I'm not making use of any scalar. The scalar serve as the what? As the identity itself, which is one, multiplying the element I just picked from the module itself, from the left our module itself, which is an abelian group. So if you multiply any element with an identity value, you should know that that will also give me the element back. That will be equals to M. I can have an identity in matrix. Suppose I want to take this into a vector space now. This identity matrix one, which can still be seen as this, is an identity element. This is an identity element in under vector spaces. And this represents an identity element of 2 by 2. That is 1001, right? If you multiply this thing with any other matrix, that means if I want to consider matrix A now, this is an identity matrix. Let's say it is 1001. And I want to consider an element from a particular module M. Okay, let's say I want to pick a matrix 2 3 1 4, which is a member of a particular abelian group M. So that means if I want to okay, this is our small m now. Our small m now is equals to what I just assumed over there, 2 2 3 1 4. So if I go ahead and multiply I and m, the identity element and the element of from element that is being picked from the abelian group, if I multiply them together, what am I going to have? 1001 times 2 3 1 4. If you multiply this together, this is m, you notice that the result will give you m back. It surely give you m. Go and try it. This multiply this, add them together. 1 times 2 is 2, plus 0 times 1 is 0. So it's 2 plus 0, that is 2, which is correct. If this multiply this, I will have 1 times 3, which is 3. 0 times 4 is 0. 3 plus 0, that is 3. So you still have m back, which satisfy this expression here. So if you can actually show this first four, then you are good to go. So what I notice here is that most of the things I did, most of the scalars, most of the scalars multiplication I did was towards the left part, while it's towards the left part, while the element of the modules are actually on the right part. So I'm only considering to know where to put it, to know to differentiate between the left hour module and the right hour module, is that your scalars will always remain on the left. Please always take note. If you look at it now, most of my scalars that I use is actually on the left throughout the list of the four axioms I want to present. You see that, looking at this, I have my element, which is and the element I pick from the abelian group or from the left hour module is actually on the right. So I'm not considering this right part. So most of the scalars that you brought in, if I want to use r, okay, you can say r open bracket m plus n. Not that you say m plus n then r at the right. If you are doing that, that means you are actually giving definition for right hour module. Do you understand that logic? If you understand this now, you can easily give me that of right module. So now if you have this now, I have A is a scalar, is on the left. That's why we are considering the left out module. A plus B is also a scalar. I added the scalars together. This is just a single A. Now in the second part, I want to add it. In the third part, I find the product. Scalar A, I considered two scalars, I added it. I considered two scalars here, I multiply it, then I took just a unit here. So I think that ends definition for the left out module. But take note, for left, you only have all the scalars on the left. For right, you always have all the scalars on the right. So similarly, if I want to show the right out module now, just asterisk, and then what are you going to say? You use the same statement here. Here this I said a left out module, or you say left module over R is an abelian group M together with a scalar multiplication. Show this expression here which satisfy the following left M1. So let's do the same thing. Let's do something similar for our right module. So something similar would be a right our module. I hope you are following. It's not something that is really hard. So just understand the logic. A right our module, or you call it a right module over R over a ring, over an arbitrary ring R, is an abelian group. You see, I'm actually writing the same thing. Is an abelian group, okay, together with a scalar multiplication. You see, it's not a must to cram. When you understand, you should be able to put down something. Just understand one, you'll be able to keep the other one. Is an abelian group together with a scalar multiplication, like I said, with a scalar multiplication. So what kind of scalar multiplication are you using? With a scalar A. So I'm still using A in this case. With a scalar multiplication A, such that the um the arbitrary ring together with the abelian group R, with the abelian group M, we always map to um the module M itself, which satisfy, I think this was what I have written before, which satisfy the following axioms, just like the way we have it for the left, um which satisfy the following axioms in that case. So what are we going to do now? Then you list out the four axioms. One, two. So I want you to understand the concept now. Three, then four. So now what am I going to write? I'm considering right out module in this case. That means I'll write right module one, such that I'll write the second part, the second axiom, and the right out module for three. Okay, I'll put the such that sign, and the right R module for 4. So then, when you looking at this now, mind you, we are considering the right R module. That means all the scalars will not be on my left part. So for the first condition, I will consider two elements, right? I need to consider two elements from the abelian group M, and that abelian group is a right module. If it's a right module, I'll consider two elements from it. Then I'll just pick one scalar. So how will you give an extraction to this? I said for the first one, you need to add this. If you have two elements now, that means you have to add it together. So am I going to add it on the left or on the right? That means, to understand the concept, for right module, I need my scalar representation to be on the right, while the element of, is together, is a multiplication, is together with the scalar. This is it. So this is together with the scalar, that means the scalar will be on the right, while the element I just picked from the right R module, which is an abelian group, will be on the left part here. So I'm only considering that, okay, scalar will always be on the right. Just take note. Okay, so that means if I have two elements, what can I do with it? I can add it in this case. What can I do on the second part? Like, I'll just go ahead for the second part. I'm only considering just one element from the right R module M, which is an abelian group. I'm only considering just one element, and then I believe I'll you remember that I said we are considering two scalar representation for the second part. So that means in this case now, since I have my scalars on the right and I have two elements, I'll go ahead and add them together, A plus B. So what am I going to put here? I only have one element under um the abelian group that I just picked. So that will just be just single M. So I'll have this as M open bracket A plus B. So you know that this should actually be equivalent to something of M times A, which is MA, then plus what? Plus NA in that case. What would this one give us? This one will give us MA then plus what? MB. Do you understand that logic? So that's just how it works. So I think for this third part, that's where I will now have product of the scalar. I have just single A, I have two scalars, I also have two scalars. I have this addition. Here in this case I also have two scalars, right? I only pick one element from the abelian group. So in this case now, that means how will I represent this now? So since I have two scalars, I can't go ahead and add again. I already added it here, so I'll just go ahead and multiply. Then I'll have my m element here. So if looking at this, how can you also, this is also equivalent to, okay, I only consider the first and last, the second and the last. So the other option I have left is to pick the first and the second while the b remain outside there. So that is how it works. And as for the last part, which is the identity, um that should be the identity assumed, which says that, okay, where will my scalar be? Will my one be on this side or on this side? So it's going to be on the right part since the scalar is always on the right. So times m. And if you do this, it will always give you, I'm using dot to, it will always give you m back. So and this ends the definition for modus. So if you say anywhere that it asks you to define modus, you should just go ahead and define the right and the left how module. And that defines it. So in this case now, um we can actually adopt the convention or the convention that we have under modules, which as for the left out module, we can actually simply mention the right out module, or probably, okay, you can go ahead and explain the two. That will be the best. Just state the two. I will advise you to state the two to be on the safer side. So I think that's enough for now based on the definition. So any other thing we want to explain after this should be like theorems and then theorems and proofs. That will just be the only thing that we have left in that case. We have a lot of theorems that you can actually consider. We have a lot of theorems that you can consider. Or we can just say, okay, if you can actually state the theorem, you can actually state it with proof too. But at first you must understand this definition. So same thing, if you after this theorem, then we need to consider that of submodus. Submodus, I will also try to give the definition of how it looks like. In submodus, we always consider a non-empty subset n. Okay, that's what we always consider in a submodule, a non-empty subset n. And at the same time, okay, we consider a non-empty subset n of an R module M. Okay, and then you can actually say is a R module if it satisfy, you actually pick a small element from this big one, you also pick another small element from this um non-empty subset. So it actually satisfy this can be called a R module if this condition hold, if the subtraction of this element and from this non-empty a non-empty subset n that we just pick, if it's actually a member in the big N itself, if this is the image in that case, this is the member of n in that case. And at the same time, if you pick a scalar r, okay, pick a scalar r where r is a member of real numbers in that case, you pick a scalar r that multiply this element that we just pick in that natural number n in that case, if it's also a member of n, that's when we can actually say that a submodule exists. You can actually call that a submodule in that case. I think this is just definition. We have a lot of things to consider under the submodule also. We have a definition for that. But I'll make sure I explain that clearly. I'll make sure I explain that clearly. Just take note of that. But all I can just say is that most of the theorems you might not end up making use of them, but at least you must understand the most important ones that we need. So I think that's all for now. So in the next video, I think this I've actually explained submodules in this case. So let me just give you the clear definition for submodules. Let me just give you the clear definition for submodules. So in case if you have been asked to define a submodule. So in this case now, for a submodules, okay, the definition. Let me just state the definition. How does it works? Okay, we can actually say, okay, let's let's say we have a non-empty subset which is n. Okay, And this non-empty subset is actually from an R module M itself. So a non-empty subset N of an R module M is called a R module. It's called a R module. Okay, or okay, if you don't call it an R module, you can say okay, a non-empty subset N of an R module M is called a submodule. Okay, if you don't want to use that, you can say okay, no, you have to define submodule, right? A non-empty subset N. Please always consider a non-empty subset N of an R module M. You are familiar with this now. We have an R module M where we have the left and the right. So we are now picking a non-empty subset N from that R module M. So this non-empty subset N of an R module N is actually called this thing exactly here. It's called a submodule. Since you're actually picking this from the R module itself, so this should be a submodule. You can call this N a submodule. So this N is a submodule initially, but it must be a non-empty subset. Please take note. It must be a non-empty subset from this. Since this N is a subset of this one, then you can now say okay oh, a non-empty subset N is called a submodule. Under what condition? If let's say if there exists a small element N which is inside the non-empty subset, and we also pick another small element M. We pick a small element M from that R module itself, such that such that these two condition holds, such that we can actually subtract M and N. After subtracting M and N, we now notice that it's also a member, or we also notice that it also exists under the what? The non-empty subset of M. It must satisfy these two axioms, okay? And at the same time, what if and at the same time, let's say we now have maybe let's say we have a scalar R from nowhere. Let's just say we have a scalar R, then multiplied by this particular small element that is being picked from the non-empty subset N. So that means if I multiply a scalar and the element I actually have there, it will also exist in the what? The non-empty subset N. So then for all R is a member of real numbers, okay? For all real numbers, for all R, the scalar I pick must be a real number, and at the same time, the M and N I pick, okay? That means let's say the M and N that we pick, let's say it should be in N. Please take note of that. Not this. It is such that N and M is in N. Mistake. Let's confirm. Let's use this. So we are not considering any element from the. If I'm picking M to be from N, if I'm picking this small M to be from that means I'm still relating something like okay, N is a subset of N. So that means this will surely affect this. So let's just pick two elements, M and N, theta, from the non-empty subset that is being picked from an R module M in that case. So it will satisfy these two conditions. If you can state this, then you define submodules in that case, simple as ABC. So then if you can actually define a submodulus, you must be able to state an example. There's an example under it too, and at the same time, some theorems under it. So how will you know the important theorems to consider? I already said it. I will try to bring in a PDF on this page, maybe in the next video lesson. Okay, I'll try to present a PDF here whereby the theorems I'll just tell you the important ones, then explain them, and then from there we move. So I think that's just the best thing for us to consider. So for the linear mapping, for this linear mapping that is here, I will need to consider for this linear mapping, that means I will have to consider a very I would like to pick three examples under this, then explain it clearly, like three examples. So in our next video, I'll make sure I do that clearly. So thanks for watching.